Hello, my name is Dr. Mel Beatty. Thank you for joining me on this lecture on the medicinal chemistry of diuretics. At the end of this lecture, you should be able to know the five major groups that diuretics can be classified in, recognize the chemical structures that allow the molecules to produce diuresis, identify the biological target of these diuretics and their mode of action, and be able to explain how modifications to the structure of the diuretics affect their activities. Now, diuretics are chemical compounds that work by increasing the volume of urine and urine output from the kidney. And here we see a picture of the kidneys. Now, by that definition, water is actually one of the earliest known diuretics. The more water you drink, the higher the urine output will be. Under normal physiological conditions, the kidneys maintain a homeostatic balance between water and electrolytes, as well as excrete water soluble products from metabolism. One of the goals of metabolism is to convert molecules into water soluble derivatives so that they can be excreted through the kidney. Now, looking at this picture here of the kidney, blood is filtered through the glomerulus, and the filtrate travels from the glomerulus to the proximal convoluted tubule, then to the descending loop of Henle. It goes through the ascending loop, reaches the distal convoluted tubule here, and then gets to the collecting duct. So there is these five places that we need to keep in mind as we take a look at how diuretics work to affect how the kidney and the nephron function. The proximal convoluted tubule, the distal convoluted tubule are places that we'll take a look at. The loop of Henle is another place that we'll take a look at as we look at where the diuretics work, and the collecting duct is another place. Okay, so proximal convoluted tubule, descending loop, ascending loop, distal convoluted tubule, and finally the collecting ducts. All right, so let's take a look at diuretics and the five different classes of diuretics and give an introduction as to where they actually work. As I've mentioned before, the diuretics can be classified in five different groups. Those classifications depend on the mechanism of action, the site of action, their chemical structures. So, osmotic diuretics are active mainly in the proximal convoluted tubule. They promote diuresis through increasing the osmolarity inside of the tubule. Then we have carbonic anhydrase inhibitors. Carbonic anhydrase inhibitors, as the name indicates, inhibit the activity of an enzyme called carbonic anhydrase. Then we have loop diuretics. Thiazide diuretics first. Thiazide and thiazide-like diuretics. The thiazide and thiazide-like diuretics are named because of the structure that they have, and we'll take a look at the structure in the coming slides. They produce most of their effect in the distal convoluted tubule. Then we have the loop diuretics, which function on the loop of Henle, specifically on the ascending loop of Henle. That's where they have most of their activity. They also have activities in other portions of the nephron, but we'll focus on their activity on the loop of Henle. And finally, we have the potassium-sparing diuretics. In this group, we have included in that group the aldosterone receptor inhibitors. All right, so let's take a look at some of these diuretics and get a better understanding of their mechanism of action and their structure. The first class of diuretics that we'll take a look at are the osmotic diuretics. Osmotic diuretics are low molecular weight compounds that are filtered through the Bowman capsule but have limited reabsorption. So they're not readily reabsorbed. So they're filtered through the Bowman capsule, they're not readily reabsorbed, and in doing so, they increase the osmotic pressure inside of the tubule, causing water to pass from the body to the tubule. They are not commonly used in the treatment of hypertension. What they do is they They are filtered through the glomerulus, and then they increase the osmolarity inside of that tubule, which then causes water to move from an area of less concentration to an higher area of higher concentration. And so this leads then to a diuretic effect. Some of the molecules that are shown here have a lot of things in common. The first thing that they have in common, beside urea, is the fact that they are polyols. They have multiple hydroxyl groups, which allows them to be water soluble. As you can see, there are also low molecular weight compounds, which allows them to be filtered. One thing to note here is that isosorbide is actually a bicyclic form of sorbitol, and those compounds are mainly used in the treatment of glaucoma now. So they don't really have a use in the treatment of hypertension, but for the sake of completion, I need to mention them in this discussion of diuretics. Now let's talk about carbonic anhydrase inhibitors. Carbonic anhydrase is an enzyme that is responsible for the formation of carbonic acid from carbon dioxide and water. When the enzyme is inhibited, it causes lesser exchange of hydrogen ions for sodium ions in the kidney tubules. And since most of the sodium remains in the urine, remains in the tubule, then it takes with it water. Water follows sodium. And bicarbonate ions are also excreted in the urine. It is worth noting that carbonic anhydrase has some other physiological relevance in other cells of the body, such as in erythrocytes. Now, inhibition of carbonic anhydrase by sulfonylamide causes an increased sodium excretion in the urine. These carbonic anhydrase inhibitors mainly act at the proximal convoluted tubule, but they're not very effective because most of the sodium that they will cause to be excreted is actually going to be reabsorbed in the further down the kidney. So overall, carbonic anhydrase inhibitors only increase the sodium excretion by about 2%. Well, only by about 2%. Today, they're mainly used to treat glaucoma, and one of the main side effects is systemic metabolic acidosis. As you can imagine, if you are losing a lot of bicarbonate ions through the urine, bicarbonate is one of these ion that actually helps with pH balance inside of the body. The more of the bicarbonate you lose, uh, the less you have it available to balance acidosis inside of the body. So one of the side effects is systemic acidosis. Carbonic anhydrase inhibitors were discovered when their sulfonylamide moiety were found to render the urine of dogs alkaline because of their inhibition of carbonic anhydrase. So these molecules were observed when they were given to dogs. It was found that somehow they made the urine of the dogs alkaline. In studying the mechanism of action, it was found that they actually inhibited the enzyme carbonic anhydrase. Now, in addition to making the urine of dogs alkalines, it was also found to produce diuresis. Now, large doses were required to actually produce the diuresis. So, it was reasoned that the synthesis of more acidic sulfonamides will offer better diuresis by binding more tightly to the enzymes. Um, those drugs actually work best when the majority of the carbonic anhydrase is actually inhibited. Upward of 90% of the carbonic anhydrase enzymes are inhibited. Now, although compounds such as acetazolamide can cause an increase in sodium excretion in the proximal convoluted tubule, most of the sodium is going to be reabsorbed in the ascending loop of Henle. So when you take that into consideration, the fact that the carbonic anhydrase inhibitors, first of all, although they increase the sodium excretion, most of the sodium is going to be reabsorbed in the body. Number two, they actually cause systemic acidosis because they get rid of so much bicarb in the urine. The risk benefit for this drug is really not worth you being used to treat hypertension. The drugs are currently being used to treat glaucoma, but not really used to treat hypertension. So then this leads us to the next category of drug that we're going to take a look at here, which are the thiazide diuretics and the thiazide-like types of diuretics. When it comes to the thiazides and thiazide-like diuretics, it is worth mentioning that these drugs were discovered in part as an effort to synthesize benzene disulfonamide derivatives of the carbonic anhydrase inhibitors that were already on the market. So the further studies that were undertaken um, to design benzyl disulfonamide derivatives led to the discovery of thiazide diuretics. Now, those thiazide diuretics actually are not really great carbonic anhydrase inhibitors. They are weak carbonic anhydrase inhibitors. Um, and it was also found that there was an unexpected ring closure. If you look at the diuretics that I'm showing you here, especially the benzothiazide ring, you realize that it's a bicyclic ring. It's a closed ring. So it was actually found that an unexpected ring closure occurred when the amino group was acetylated, which it led to a ring closure. Now, again, although the compounds were originally designed as carbonic anhydrase inhibitors, it was found that they really exerted their diuresis through a completely different mechanism. In here, their site of action is mainly the distal tubule, not the proximal convoluted tubule, as we've seen in carbonic anhydrase inhibitors. And also, they actually bind to the sodium chloride cotransporter. They bind to the sodium chloride cotransporter, and they are weakly acidic compounds. So let's take a look at what makes those compounds acidic and what that acidity actually adds to the property of those molecules. So taking a look at the acidity of the thiazides and thiazide-like diuretics, um, the the acidity of the molecule is really determined or controlled by two different positions: the N2 position and the substitution of the sulfonamide at the N7 position. Okay, the hydrogen at the 2N position is the most acidic because of the presence of the electron withdrawing effect of the sulfone group right here. So the hydrogen at the N2 position is the most acidic because you have the effect of the electron withdrawing sulfone group at this position. Now, the sulfonamide group that is substituted at the C7 position also provides a level of acidity, but it is less acidic than the N2 position. Now, every time you bring acidity or even you bring a basic nature to a drug, it immediately increases its water solubility because of the ability to ionize and also to engage in hydrogen bonding interactions. So the presence of these two hydrogens on the acidic moiety allows the drug to be more water soluble. So the water solubility of the drug is enhanced by the presence of those two groups. Now let's take a look at what position 6 and 7 also bring to to this particular moiety here. So as we've mentioned already, at position 7, we have a sulfonamide group. Let me begin with position 6 and then we'll move in order. So the 6th position is key to the activity of the thiazide because it requires the presence of an electron withdrawing group. So the 6th position here can have a chloro group or a trifluoro group. But this position is key because in order for the drug to be active, in order for the drug to be to actually serve as a good diuretic, it requires the presence of an electron withdrawing group at the 6th position. Okay. Now, the presence of an electron donated group, such as a methyl or a methoxy, is actually completely going to reduce the activity. So, if you were to replace that chloro group here with a methyl group or a methoxy group, that will reduce the activity of the drug. So, you need to have an electron withdrawing group here. And as I'm speaking, you guys need to start thinking about possible exam questions or quiz questions. Possibly, I could draw a structure of this molecule here and simply change the chloro group with a methyl group or a methoxy group and put it in a question asking you, would you expect this molecule to be more active than the one with the chloro group? So if I was to draw this molecule and then draw another one with a methyl here, and draw another one of the methoxy group, I could ask the question, which of those molecules do you expect to have the most activity? So you need to start thinking in terms of structures, in terms of molecules. What does the molecule look like? When we modify at such or such position, what happens there? Now let's talk about position 7. At position 7, the molecule loses its diuretic properties upon removal of the sulfonamide group at position 7. So if we lose that sulfonamide group here at position 7, we lose the diuretic properties of the drug. The sulfonamide position at position 7, the sulfonamide group at position 7 is key. It's essential to the diuretic property of this particular drug. So these are things that are really, really important for us to remember as we continue looking at the structure activity relationship of thiazides and thiazide-like diuretics. Now let's start talking about some other changes in the molecule that help to increase or decrease the activity of diuretic. The first thing we want to talk about here is lipophilicity. Placing a lipophilic group at position 3 also increases diuretic activity. Now, I know some of you are wondering, what's position 1, what's position 2, 3? Position 1 is right here. Position 2 is at this position, and this is position 3. So placing a lipophilic group at position 3 increases the diuretic activity. Okay. Now let's talk about saturation. Saturation of 3 and 4, increased diuretic activity is seen with saturation of the double bond. So when you have 1, 2, 3, and 4, increased diuretic activity is seen with saturation of the double bond. Okay, when the double bond is saturated, you have an increased diuretic activity. As far as the N2 position is concerned, when you have alkyl substitution at the 2N position, that also increases lipophilicity and the duration of action. So if you were to put an alkyl group substitution here at that 2N position, that will increase lipophilicity and duration of action. Okay, now let's continue working with this here. Now, when you look at the quinazolinone derivatives of thiazide diuretics, those are basically analogs of the thiazides, but instead of the sulfone group, you have a ketone group. Instead of the sulfone group, you have a ketone group. Another way to put it is to say that the sulfonamide group has been replaced with an amide group. It's another way to put that. The effects of the drugs in this category are very similar. The effects of the drug are very similar, and the drugs still are going to bind to the cotransporter and are going to have the same effect as the thiazide-like drugs. So the key here is this. This is a quinazolinone derivative of the thiazides, and the representative is metolazone. Metolazone is a representative of this class of drugs. It is similar to the thiazides in activity. Most practitioners simply refer to them as thiazide diuretics without really stepping into the difference here between thiazide and thiazide-like diuretics. They have a longer duration of action because they bind to proteins. So they have protein binding interaction, which gives them longer duration of action than the thiazides. Now, one of the reasons why they bind, why they also have long duration of action, is because they are 50 to 7% bound to carbonic anhydrase in the erythrocytes. We've mentioned earlier that carbonic anhydrase was present and had other physiological relevance in other parts of the body. So 50 to 70% of these derivatives of metolazone are actually going to be bound to carbonic anhydrase in the erythrocytes. Another group of thiazide-like diuretics are the phthalamides derivatives. The phthalamide derivatives are represented here by chlortalidone. The difference between these drugs is really the fact that instead of having the benzo diathiazide ring, the chlortalidone and these types of molecules have the phthalamide structure instead. These are extensively bound to carbonic anhydrase in erythrocytes, and their mechanism of action is very similar to that of the thiazides as well. Finally, the last group that we're taking a look at here in the thiazide-like diuretics are the indolin derivatives. The indolin derivatives are represented here by indapamide. The indolin derivatives and indapamide are the only ones that do not contain, they only contain one sulfonamide. You notice here they only contain one sulfonamide. They do not contain a thiazide ring at all. Do not contain a thiazide ring, contain only one sulfonamide, and they also are bound extensively to carbonic anhydrase in erythrocytes, and they lead to longer duration of action. Now, so we've taken a look at the thiazide drugs and the derivatives. Again, they have the same mechanism of action, but when those drugs do not have the same benzodiazide structure, they are called thiazide-like diuretics instead of thiazide diuretics. In all honesty, most practitioners don't really make the difference between the two. Um, as a medicinal chemist, we tend to be a little pickier. But as a practicing pharmacist, really what I'm concerned about is the effect that the drug is going to have. So for all intent and purpose, those drugs can be lumped into the same category and be called thiazide drugs because they have the same mechanism of action as the original thiazide drugs that were designed. Okay, so quick recap here. Thiazide drugs were designed as a way to improve carbonic anhydrase inhibitors. In the process of designing those drugs, it was found that they actually did not even have high affinity to carbonic anhydrase inside of the nephron, but they were actually binding at a different site and causing diuresis by a totally different mechanism. And so we've taken a look at the thiazide diuretics and the different classes that comprise that group of drugs, and they have similar mechanism of actions, although sometimes the structure can be different. Now let's take a look at the loop diuretics. The loop diuretics are also called high ceiling diuretics. This class of drugs that we've the classes of drugs that we've studied so far have been classified based on the structural similarities or the mechanism of action. So carbonic anhydrase, we classify them as the mechanism of action. They inhibited carbonic anhydrase, or osmotic diuretics. Um, thiazide diuretics were classified based on their structures. Now, the loop diuretics are classified based on where they actually operate, where they have their action. So they're classified based on the location of their action. They all act on the thick ascending limb of the loop of Henle. And in the thick ascending limb of the loop of Henle, they are going to inhibit the sodium potassium chloride symporter. So they act on the thick ascending limb of the loop of Henle and they inhibit the sodium potassium chloride symporter. Okay. They also have possible effects on the proximal and distal tubules, but for the main place where they will have their effect will be on the ascending limb, the thick ascending limb of the loop of Henle, and they will inhibit the sodium potassium chloride symporter. All right. So here shown in the pictures here, we have furosemide, torsemide, bumetamide, and ethacranic acid. Now these are derivatives of intranilic acid or O-amino benzoic acid, and we'll take a look at intranilic acid in the next slide here. Now, let's focus in on furosemide. So, furosemide is an intranilic acid derivative, okay? Intranilic acid derivative. Now, this structure here is a 5-sulfamoyl intranilic acid. So, you have a 5-sulfamoyl intranilic acid here. So, intranilic acid is drawn here, And furosemide is a derivative of antranilic acid. It is a high ceiling diuretic that was discovered to be the most potent of a series of five sulfamyl antranilic acid derivatives. As seen in other classes of diuretics, the chloride and the sulfonamide moieties have been retained in the synthesis of furosemide. That's a very important factor. Oftentimes, when we teach those classes, we are asked, why do you bring into consideration, into discussion, drugs that are no longer in use? Medicinal chemistry cannot be taught in a vacuum. It has to be taught based on the history and the design of the drug. There is no structural activity relationship if you don't compare the activity of the drug with predecessors. And so in this particular case, you will notice that furosemide is a different class of drug. Furosemide acts on a different place, namely in the ascending loop of Henle. But all of the lessons that were learned from the design of the carbonic anhydrase, the lessons that were learned from the design of the thiazides, have been retained here for the synthesis of furosemide, with the chloro group being maintained and the sulfonamide group being maintained as well. Now, those compounds are more acidic than thiazides because of the presence of the carboxylic acid. They're more acidic than the thiazides. Now, the second loop diuretic that I would like to mention here is bumetanide. Bumetanide is unique with the presence of the electron withdrawing phenoxy group instead of the chloro or fluoro group. As you remember, we've talked about how having electron withdrawing groups are important, but changing the structure of the molecule as significantly as we've done here with bumetanide, we actually have the electron withdrawing phenoxy group right here, electron withdrawing phenoxy group, as opposed to a chloro or fluoro group. Now, also a difference with bumetanide is the fact that the amine has been moved one carbon away. Okay, the amine here has been moved one carbon away from the carboxylic acid substituent. When you look at the 5-sulfamyl antranilic acid, the amine and the carboxylic acid were actually very close together. In the case of bumetanide, the amine has been moved one carbon away from the carboxylic acid substituent, and this led to an increase in the diuretic potency. This led to an increase in the diuretic potency. Very, very important fact here to remember. So this gives you an idea of how moving and changing things inside of a structure can already increase the activity or decrease the activity of a particular molecule. In this particular case, we have moving the amine group one carbon away from the carboxylic acid, and also introducing the phenoxy group instead of a chloro or fluoro group, which have allowed bumetanide to have a higher increase in diuretic potency. Now, further modifications from furosemide led to the development of torsemide. Torsemide is different from furosemide because there is a presence of a sulfonyl urea as opposed to a sulfonamide. You have a sulfonyl urea as opposed to a sulfonamide. Now, the drug does not act on the proximal convoluted tubule, and it doesn't increase phosphate and bicarb excretion as much as furosemide would. So the main difference with if you want to compare torsemide and furosemide, both of the drugs are sulfamyl antranilic acid derivatives. Okay, the main difference is instead of a sulfonamide group, you have a sulfonyl urea group. Okay, and that drug does not also attack on the proximal convoluted tubule. Now, I have one last loop diuretic that I would like to mention, and it's ethacrynic acid. Ethacrynic acid is the only loop diuretic that does not contain a sulfonamide derivative. It belongs to the phenoxyacetic acid group. So it doesn't contain any sulfonamide derivative. It doesn't contain a sulfonyl urea derivative. It belongs to the phenoxyacetic acid group. Now, it was designed to react as a Michael acceptor with sulfhydryl containing enzymes and cause their inhibition. But studies of the mechanism of action seems to show that the mechanism of action is actually a little more complicated than we anticipated. Because even in the absence of the double bond here, the drug still has activity. In research, the best diuretic activity was observed when the oxyacetic acid group was placed para to the alpha beta unsaturated ketone here. So this is the oxyacetic acid group was placed para to the alpha beta unsaturated ketone. So the best diuretic activity was observed in those positions. In addition, hydrogen atoms on the terminal alkenes provided maximum reactivity. It provided maximum reactivity. So quickly to recap this here, ethacrynic acid doesn't have even a sulfur group in it, doesn't contain a sulfonamide derivative. It's a departure from the earlier designs that we've seen, even coming from the carbonic anhydrase inhibitors through the thiazide diuretics and looking at all the other loop diuretics. It's the only one that doesn't contain any type of sulfonamide derivatives, whether it's a sulfonamide or a sulfonylurea. And so it belongs to a phenoxy acetic acid group. Okay, you have a phenoxy acetic acid group here. Again, it was designed to react as a Michael acceptor, but its mechanism of action seems to be a little more complex than thought. And finally, the presence of the hydrogen atoms, not shown here, but hydrogen atoms on the terminal alkene provided maximum reactivity. All right, so we'll conclude this with some additional structure-activity relationship for the loop diuretics, and then after that we'll jump into the potassium-sparing diuretics. So I've numbered these molecules here for you, and I'm showing furosemide and bumetanide. You can see the structural similarities between those two. You can see the structural similarities. You can see that in bumetanide, the amino substituent here has been moved one carbon away from the carboxylic acid. You can also see the presence of the hydrogen donating group as opposed to the hydrogen withdrawing group here at position 4, and also the fact that they both have the sulfonamide derivative here at position 5. So let's begin with this. The substituent at position 1 must be acidic. Okay, substituent at position 1 must be acidic. If you lose the acidity, you lose the activity. The sulfamyl group at position 5 is essential for activity when it comes to furosemide and bumetanide. Okay, the sulfamyl group at position 5 is essential for activity. Substitution of the amino group, when it comes to the 5-sulfamyl 2-aminobenzoic acid, so when it comes to furosemide, substitution is allowed. Substitution is allowed, but is limited to furfuryl, is limited to benzyl or thionyl methyl groups. Okay, so substitution is allowed, but only limited to those groups that we just mentioned. When it comes to bumetanide, to the 5-sulfamyl 3-aminobenzoic acids, substitution is allowed without much change in the activity. So we can change, we can have substitution or changes at this amino group here, and that will not change much in the activity of the drugs. So this concludes the part of our lecture on the loop diuretics. Now, most of the diuretics that we've taken a look at today, most of them are going to, in addition to causing you to lose sodium, also will cause you to lose potassium. And so in order to prevent loss of potassium, the thought of potassium-sparing diuretics arose. So let's take a look at these potassium-sparing diuretics. Now, there's two groups of potassium-sparing diuretics that we'll take a look at. The first group that we're focusing on are the mineralocorticoid receptor antagonists. Okay, And those are actually going to bind to the same receptor that aldosterone binds to and prevent aldosterone from having its effect. Now, aldosterone is a powerful mineralocorticoid. It is secreted by the adrenal cortex, and it promotes salt and water retention and potassium and hydrogen ion excretion. Okay, so aldosterone is going to promote salt and water retention. At the same time, it's going to promote potassium and hydrogen ion excretion. Once excreted, or once secreted, aldosterone is going to bind to the mineralocorticoid receptor. Okay, it's going to bind to mineralocorticoid receptor, as we can see here in this picture. So it binds to mineralocorticoid receptor. Okay, and the way it's going to bind to mineralocorticoid receptor is going to interact with a methionine amino acid with its C7 hydrogen, a C7 hydrogen. Okay, C7 hydrogen. So the C7 hydrogen is this hydrogen here at this position. Okay, so the aldosterone antagonists actually have a substituent at that position. If you look at spironolactone here, there's a substituent here, and eplerenone also has a substituent at that position there. Additionally, the presence of the lactone ring at the C17 position, you have the lactone ring here, at the C17 position, is necessary for the activity of the antagonist. These are the two main compounds, spironolactone and eplerenone. Okay, so the C7 position has to be protected because it interacts with the methionine inside of the binding pocket with the receptor, and that's what causes the activity of aldosterone. So a substituent is installed here to prevent the interaction of the C7 position with the methionine. Now, spironolactone is metabolized to its active metabolite, canrenone. And I have here, canrenone is this structure that's listed here. It exists in equilibrium with its salt form, canrenoic acid. In addition to binding to the mineralocorticoid receptor, spironolactone also binds to the glucocorticoid receptor, the androgen receptor, and the progesterone receptor. Its interaction with the androgen receptor is the underlying reason why spironolactone has possible sexual side effects. So you see often with spironolactone gynecomastia, decreased libido, and impotence. Eplerenone is more selective for the mineralocorticoid receptor. It therefore does not have any of the sexual side effects associated with spironolactone. Structurally speaking, eplerenone has many of the similar structures, similar features of spironolactone, but there's the key difference there is the fact that eplerenone has an additional epoxide. I believe it's a 9 alpha and 11 alpha position. So it has an epoxide at this position, which prevents it from binding to the androgen receptor and to all the other receptors that androgen receptor, progesterone receptor, and glucocorticoid receptor. So the presence of this epoxide is key in preventing eplerenone from having the sexual side effects that spironolactone has. Eplerenone was actually designed as an analog of spironolactone that will have less of the side effect that spironolactone had. Okay. The other groups of potassium-sparing diuretics that I wanted to mention here are amiloride and trimethoprim. Those two drugs are in the class of potassium-sparing diuretics. They are rarely used alone because they only have mild diuretic effect. They are often used in combination with thiazide diuretics or loop diuretics. Both drugs are weak organic bases. They can bind to negatively charged regions of the sodium channel and inhibit the epithelial sodium channel. The greater the potency of amiloride is due to the fact that it is a stronger base. Because of this moiety here, it is a stronger base. In summary, those drugs are actually going to block the reabsorption of sodium ion and inhibit the secretion of potassium. They result in an increased sodium and chloride excretion and no loss of potassium. Okay, so that's how these drugs are actually going to work. key here is that they're both weak organic bases that combine to the negatively charged regions of the sodium channel and inhibit the epithelial sodium channel. So in summary, today we've reviewed the 5 classes of diuretics. If you've noticed, I've lumped together aldosterone antagonists and potassium sparing diuretics. For our purposes, they'll be um, combined in one class. We've reviewed the structural differences between the diuretics, and we've also looked at some of the similarities of these diuretics. We were able to identify the site of activity and the mechanism of action of the drugs, and we've covered how key structural changes affected the activity of the drugs. For those of you that would like to do a further reading, I will recommend Access Pharmacy that's available through the Malfer Library. And I've also put one of the books that I've used in preparation for this lecture here, and it is cited on this slide here. Thank you so much for your attention. I will put together another video with examples of potential questions that I can use in a quiz format or in an exam format to allow you to get familiar with the types of questions that can come on an exam. Thank you. I hope you have a great rest of your day. Thank you.